let's discuss this question. The question says the pattern shown, that's the pattern here, is due to two slits. So this is due to two slits. How would the pattern be different if we double the separation of the slits, maintaining everything else the same? Okay? So the question is asking us, what if we maintain everything the same except for the slit separation, we double it? How is this pattern going to change? We are given four options. The first one here, the width of the fringes look the same, but it's darker closer toward the middle than this one here. This one here, this is where it gets darker, while this one, look where it gets darker. The second image also looks like the same fringe widths, but then it darkens further away from the center. This is where it darkens, at the edges of the picture. The third image, we have wider fringes. They get wider than what we have here. And the last one, we got narrower fringes. Now, to answer the question, we need to consider the expression that we use for the width of interference fringes. Now, the expression is given here. Delta y is lambda L over d. Delta y is the actual width of the fringes. Now, for example, if we were given a scale, we could measure it off this image here by counting how many fringes would fit in that scale. That's our delta y. It is the distance separation a dark fringe from a dark fringe, this one here from this one here. An interference minimum, or a dark fringe of light, to the next fringe of light. That's delta y. It is also the distance separating the middle of a bright fringe, or a bright maximum interference, to the next bright fringe, again from the middle. That's my delta y. Lambda is the wavelength of light. In this case, it would be correspondent to the green light that we see. L is the distance separating the slits from the screen, from this image here. That's what L is on the numerator here. D is the separation of the slits. That's what they tell us is going to change. That's the only thing that's going to change. By examining the expression, you notice that the only thing that's going to change is in the denominator. We are going to double it. Doubling D means we are going to have a 2 here in the denominator. That means we are going to have delta y. So the effect of doubling the separation of the slits D is going to be to have the fringe width delta y. So the only image that corresponds to that would be the last image here, where we see narrower fringes. Part B of the question asks, how would the pattern be different if we double the width of the slit, maintaining everything else the same? That means we are going to maintain the wavelength of the light the same, the distance separating the slit from the screen the same, the separation of the slits the same. All of these are going to remain the same, except the width of the slit. Obviously, when you look at the interference equation, delta y lambda L over d, nothing should change. So if this is my pattern, I should expect to see the same interference fringes. Now these are possible in these two graphics, the first one and the second one. Both of them have the same delta y, so both of these can be appropriate. Now, where would the width of the slit have a role? The width of the slit would have a role in the diffraction pattern, in where these dark fringes here happen. Now, the diffraction pattern has fringes whose width is given by a similar expression to the one we used for interference. The expression is delta y lambda L over A. So instead of lambda L over D, it is lambda L over A. A in this case being the width of the slit. A is used for aperture. It is the width of the slit in this case. So it is the same expression, but referring to where these minima appear. Another thing you need to remember, and we'll see it in other examples, for diffraction, the central maximum that we see here is twice the width of other fringes. This expression here is given for other fringes. The central maximum is twice as wide as that. But this expression is sufficient for answering this particular question. Now, AA makes the diffraction fringes half as wide, meaning instead of having the diffraction minimum here, it should be closer to the middle. So that's figure 1. Figure 3 is further away from the middle.